we should really cement the relationship between Wilson loops and topological properties, and between elementary band representations and topological properties. So in 1D, we just, everybody remembers these are the eigenvalues of all the atomic limits possible in 1D. Well, all the elementary atomic limits or elementary band representations, same thing. Of course, I can make an atomic limit by combining any of these. Okay? And there's a one-to-one mapping between these eigenvalues and the eigenvalues of the Wilson loop, right? And I showed you how to do a one-to-one mapping with, you take, so first of all, every plus and minus that I have at 0 and pi, you take them out, and these have eigenvalues in the Wilson loop, theta and minus theta, Vanier centers away from 1a and 1b. Every plus plus or minus, every remaining plus plus, okay, has eigenvalue plus. Every remaining minus has eigenvalue minus. If I have plus plus and plus minus, what eigenvalues would this have? So if I had this configuration, for example, of bands below the Fermi level, well, these bands are clearly one s orbital at 1a, one p orbital at 1a. So s and p, these are s at 1a, p at 1a, plus plus is another s at 1a, and plus minus here is a s at 1b, right? So these can hybridize. Of course, you can hybridize this with this, whatever, doesn't matter. But these, I just choose one of them. These can hybridize, give me sp hybridization with eigenvalues theta minus theta, which is the position of the 1a. This s at 1a cannot move from 1a because it's alone now. Okay, so its eigenvalue is just 0, which is the position of in the unit cell of the 1a Wyckoff position, which is at the origin. This s at 1b is now alone. It can't hybridize with anything. It's sitting there. So it has to give me the position. The Wilson loop just tells me where it sits. The Vanier center sits at mid-bond because it's 1b. So the Wilson loop is pi. There's a one-to-one mapping from any eigenvalues, from any set of eigenvalues. And this is how you do the one-to-one mapping. If you really want to, well, if you get used to it, you can do it by eye. But otherwise, you just identify the eigenvalues, you put them in the atomic limits, and you take every s and p orbital, you hybridize it, you put it as theta minus theta, you throw it out, and consecutively, every s and p at the same Wyckoff position, you hybridize it, you put it, you take it out, and then you go down and find out all the Wilson loop eigenvalues. Is that clear? Okay. Now we move to 2D. So, the zeroth order thing that you do in 2D, you find all the atomic limits with inversion symmetry. So 2D plus inversion symmetry. Okay, that means I have a lattice that's square or rectangular. Let's not make it square, let's make it rectangular. I don't have C4, okay? Whatever. Let's identify all the maximal Wyckoff positions. And since I only have inversion, you can go and read up on what, or like remember what Barry said, and Jen and Moyes and Juan Luis about maximal Wyckoff positions. But you don't need to you don't need to remember them. You can just go and get them off the Rabal crystallographic server. But they're essentially the positions that are left invariant for this symmetry group. They're left invariant by a group that is isomorphic to inversion, by a point group that's isomorphic for the symmetry group. It's more complicated in general. So I'm going to put my origin here. What are, within the unit cell, what are the positions that are left invariant by inversion? By a group isomorphic to inversion. Is this one left invariant by inversion? Call this 1A. Is this one left invariant by inversion? So my atoms are here, okay? I'm putting my atoms here. but the center of charge can move, is this one left invariant by inversion?
Yes.
And is left, so this is left invariant by inversion. This is left invariant by inversion and in which direction? X. Call this xy. Is this one left invariant by inversion? What's its side symmetry group? Very good, thank you. So call this 2b, call this 2c. Sorry, 1b. I'm stupid, I apologize. Moise is going to kill me, I apologize. It's 1b and 1c. So they're just multiple. If I had c4, it would be multiplicity 2, but I don't. So how about this one? Is this one left invariant by inversion? What's the side symmetry group? Very good. They're all isomorphic, but they're different in the translation part. So now what can I do? I can put S or P orbitals. I can say that the Vanier centers of charge can move everywhere, and they can transform into the two representations of this group, which are equivalent to S and P orbitals, or scalar and vector representation. Yeah? So I will expect to have the following atomic limits. S at 1a, P at 1a, S at 1b, P at 1b, S at 1c, P at 1c, call this 1d. S at 1d, P at 1d. Is that clear? Yeah? Okay. So now I'm going to go to the Briand zone and ask what bands that come from, say, s orbitals at this position, or some center of charge transforming as an s orbital at this position, what are the eigenvalues in momentum space? Okay? I'm going to go through this just like I did here. Well, I'm not going to go through it. You're going to go through it. And I have a Briand zone, and this Briand zone looks like this. And I'm only drawing the gamma point, the x point, the m point, and the y point. 4 times this, right? But I'm only, okay, so these, why are these points special? I can put their inversion eigenvalues here. So, what do I, if I had a band that comes out of s orbitals or centers of charge, electrons transforming as s orbitals, s and p orbitals are just names of representations. They don't really mean, if I say s orbital here, it doesn't mean that I have an actual atom sitting there with s orbitals in it. It just means the center of charge has moved there and its wave function is transforming as this representation. So let's call these gamma x, y, m. What's s at 1a? What will its eigenvalues be? All plus. Why? Because s is the inversion eigenvalue 1, invariant, the scalar, at this position. It has no phase. It goes to plus in momentum space. What's p at 1a? What's s at 1b? Plus, minus. Very good. What's p at 1b? The p is always the opposite of the s. Right? What's s at 1c? Very good. The p at 1c is just the opposite of this guy. What's s at 1d? Very good. Okay. Now you have all the atomic limits. And you notice something about the atomic limits. The number of negative or positive eigenvalues of inversion in any of the bands in the atomic limits is what? Even. So, number of minus or plus inversion eigenvalues in all atomic limits is 2 times n, where n can be 0, 1, or 2. In 3 dimensions, this goes to 4 times n. And they're the reason for the appearance of higher order topological insulators in 3 dimensions. Okay? Okay, but we're still sticking in 2 dimensions. Yeah, so this is clear? So if I have a band that doesn't have an even number of inversion eigenvalues, what does that mean? It means either I've done something wrong, or one of my premises was wrong, and the premise was that bands that come from localized Wanny orbitals have, these are all the bands that come from localized Wanny orbitals. So the only premise that can fail is that the band that has an odd number of these doesn't come from localized Wanny orbitals, or as was mentioned here, is topological. So now, let's take the following band, the simplest band, one occupied band. One occupied band. And its eigenvalues, inversion eigenvalues, are minus, plus, plus, plus. Is this band an atomic limit? Can it be deformed to an atomic limit? No, because it's got an odd number of inversion eigenvalues. So first of all, well, there's a caveat here. You have to prove that these inversion eigenvalues are actually compatible in the Brillouin zone, which implies some sort of a usage of compatibility relations that Moyes explained last week, and that Andreas was also talking about. But basically, it satisfies this. So you first have to satisfy that bands in the Brillouin zone can actually exist. Sometimes they cannot move. For example, I cannot have a band that has 2 plus eigenvalues here and 1 here, right? Because that would mean I have 2 bands at this point and 1 band at this point. That's the simplest band that doesn't satisfy what's called compatibility relations, and it doesn't satisfy in a trivial way. But there's more non-trivial ways that I don't go into. You can check them, they're all tabulated because of the work of Moyes and Luis on the Bilbao crystallographic server. But this is an algorithm that you can just check. For the simple group that's this, it's pretty clear that you can have this band because this group is just inversion. So as you move away from a high symmetry point, you have no other symmetry characteristic of the band so any bands can connect. Okay? So you can have this band, okay? So this is not an atomic limit. So it's clearly topological. And this brings you to the 0th order, which I won't go through, but it brings us to the 0th order way of checking for topological materials. This is the simplest order way, and it's pretty clear that it's generalizable to all the groups. So what you can do is you can obtain these atomic limits for every space group, and they're now tabulated again on Moyes and Lisa's website. Okay, you can get all the atomic limits, and then what you can do is you can run a DFT calculation that Maya has run now for 26,000 materials so far, and you can look at the bands below the Fermi level, and you can just look at their eigenvalues. If I have inversion, I would just look at their eigenvalues under inversion. Okay, this is energy xy. So I have, let's say I have plus, 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 plus everywhere but here. Okay. So for this simple case, knowing the eigenvalues below the Fermi level, I could ask, can these eigenvalues be formed as a linear combination of these eigenvalues? If the answer is no, the system has to be topological. So for example, for this case, this simple case clearly is no. But you can clearly see that for this case, it's also no. Okay? And for this case, it's also no. They all have 3. Right? Is it clear that this case, with 3 bands below the Fermi level, with plus, plus, minus, plus, plus, minus, minus, plus, plus, and plus, plus, minus, can also not be described by atomic limits. It's got odd number of minus eigenvalues. So it's topological. So you can run this program on all the symmetry groups, and this is the 0th order, the simplest way you can find topological in insulators. And this is basically, if it's not a linear combination of these elementary band representations. You have to make a caveat which I won't go into. Then it has a strong topological index.
Sorry?
Yes.
Just more generalizing the procedure. When you have a bigger symmetry group, do you have to do that for every element of the group?
Yes, exactly. So because you can have, you know, the system can be atomic. So you have some high symmetry group, right? So the system has got a lot of characters of a lot of different symmetries. You have to take into account each and one of them. So at the gamma point, it wouldn't be just one eigenvalue. It would be a set of eigenvalues. But all you're running is a linear dependence. So you go into your DFT. You have a program that lets your DFT have, you know, that makes VASP give you the high symmetry point eigenvalues. You put them in a vector, okay, and you check linear dependence versus this. It's just the multi-dimensional version of this. There's nothing. This is the simplest thing, but it's just a multi-dimensional. Is that clear? It's just there's no rocket science. Once you've done inversion, well, there is rocket science in like the terms of not making mistakes, and that's actually very hard. But you know, in terms of the procedure, the same procedure with inversion happens with everything else. Okay, so this guy. So let's find out what kind of topological is it. Okay. If I have minus, plus, 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 inversion symmetry by itself tells me that this cannot be trivial. So it has to be topological. But I need a little bit more information on what type of topological thing it can be. If I lose inversion symmetry, so say I take this system with one band here, and then break inversion symmetry. The question is, do I lose the topological class? Does this system become trivial? And the answer is no, not for this system. Okay? Because this is just a Chern insulator. This is a Chern band. This is Chern number 1 band. How do I know it? Well, easy. How do I know it? Kx, ky. Right? These are the two. I'm just plotting the eigenvalues of the lowest band of the occupied band at these high symmetry points, yeah? Is it clear what I'm doing? I know it's lunch and we had like a nice tiramisu. I'm already feeling it, you know, just wake up. There's a lot more of this coming. So is it clear what I'm plotting here? Okay, good. So now I'm going to ask what the Wilson loop eigenvalue is at kx equals to 0. So at kx equals to 0, this is a 1D system as a function of ky, right? So I already know, so I can look for these inversion eigenvalues in this direction. What is the Wilson loop eigenvalue? Huh? So at kx equals to 0, so kx is just kind of a good quantum number. So for every kx, I can make this a 1D system. Now, when kx equals to 0, since inversion sends kx into itself at kx equals to 0, this is an inversion symmetric 1D system. I can read its eigenvalues. You know, I know it's got to have, you know, plus minus. So in 1D, this is an atomic limit, right? This plus minus, and it's the atomic limit with what? It's the atomic limit of p orbitals at the 1b Wyckoff position. Yeah. In 1D. So at kx. So again, logic is, I'm asking in 2 dimensions what a band that has the following eigenvalues, gamma, x, and y, plus, 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 minus, what this band represents. And I'm trying to convince you that it's a Chern number band. It's got a Chern number. Okay? Now, how am I going to convince you? Well, I'm going to plot how the Wannier center moves. Okay? So, what I'll plot is the Wannier center for every kx. The Wannier center in the y direction for every kx. Okay, so I'm going to plot the eigenvalues of the Wilson loop in the y direction as a function of kx, right? Because I have a quantum number. For every kx, I can think of it as a one-dimensional system in the y direction. And I can plot its eigenvalues. Is this clear? Okay, at kx equals to 0, I have inversion symmetry of this 1D system. At kx not equal to 0, I don't have inversion symmetry because inversion sends me to minus kx. But kx equals 0, I have inversion symmetry, and that's why these points gamma and y are labeled by inversion eigenvalues. But we already established that I have a 1D inversion symmetric at kx equals 0. We already established it in 1D. I only have trivial states, well, trivial states in terms of Vannier-izable. They have this, pi Wilson loop topological index, but in terms of Vannier states, they're trivial. So what is the state made out of minus and plus eigenvalues? You can read it from there. It's a p orbital at the Wyckoff position actually here, right? Even though this says it said 1b because I was putting it here. It's a 1c, okay? So this is p orbital at 1c. So it's got, what's the Wilson loop eigenvalue of it? Pi. Very good. At kx equals to pi, I have a 1D system that's inversion symmetric of eigenvalues inversion plus and plus in this band that I chose, which is a s orbital at 1a position. Okay? And what's the Wilson loop for this guy? 0 Wilson loop. Wilson loop is the center of Vannier of charge. So now if I plot the Wilson loop as a function of kx, so this is eigenvalue of Wilson. This is 0 minus pi, and it's clearly periodic because I have a unit cell. Once I go outside the unit cell, I go back to the next unit cell. So it's periodic, right? Where this is kx equals to 0, kx equals to 0, this is kx equals to pi. Where's the Wilson loop here? At kx equals to 0. Put this point here. Where's the Wilson loop at kx equals to pi? At 0. This is a continuous loop as I move. The Vannier centers in a gap state, they kind of go, right, as a function of kx, they do something. So there's one way of doing it. There's only one way of connecting these two. There's 2 points, angled, I have a line. Let me draw it a bit curved. Okay, I draw it like this. Okay, that's what the Vannier center will do. So what does this actually mean? Well, physically it means that if I Fourier transform in the x direction, so these are called hybrid Vannier states, okay? But it means that if I Fourier transform in the x direction, and in this direction I don't Fourier transform, okay? So I have my unit cell in this, I have my unit cell here, it's kx equals to 0. I'm just going to redraw that plot really. Kx equals to 0, kx equals to pi. My unit cell, I'll have a center of charge that here is centered on the 1c Wyckoff position at kx equals to 0. And then it's just going to go down to the 1b Wyckoff position. That's where the center of charge is going to move as a function of kx. Yeah? Okay. Now, question. I don't have the drawing from minus pi to 0. How do I get it? And how does it look? What does inversion symmetry do? So just think of y instead of theta. What does inversion symmetry do? Apply inversion on this, right? What does it do? It does 2 things. Changes what? 2 things. Changes kx to minus kx, and changes the Vannier center at y to minus y. So this is uniquely determined the flow. Of course, it could do some, it could do things like this, which would be matched by things like that here, but it doesn't matter, This is the universal. Now, clearly that winds. In the 1D Briand zone, it winds. Yes? Is it clear that it winds? You start from here. You go. Another drawing of this, if I drew it, if I drew it if I shifted it by pi, I could draw it like this. Okay? Same thing. Sorry, I could draw it. Being stupid. I could draw it like this.
But it could look like the other one.
Huh?
It could look like the
Could
other
look like this.
No, like the other one you drew first.
Yeah, but it's more. Okay. So, okay, so is this clear? Okay, so what is this? Is this clear? This is the quantum Hall state. This is a quantum Hall state because it is a quantum Hall state. But it should be clear that it's a quantum Hall state by adding unit cells in this direction. Okay? So this is within the first unit cell. This is the position of Vanier state center within the first unit cell. Okay? So I don't want to go further until who's unclear about the fact that this is the only, that, you know, given this band below the Fermi level, which I could have obtained from a DFT calculation if I got lucky, that's clearly a topological band. And what kind of topological band it is, I can just determine by determining its Wilson loop as Vanier flow center. And this is the unique Vanier flow center modulo, you know, non-universal things that I can get from these eigenvalues. Is that clear?
Okay.
Yes.
Yeah, I have a question. In this case, I mean, you are always Fourier transforming in the x direction, but I think you mentioned that you go from 1C to how do you have information about the x position?
I can do it. I can do it in the y direction too, and I'll get the same thing. Just notice I could do it in the y direction too. Yeah. Well, yeah, I could do it in the y direction too, but the information here comes at kx equals to 0.
Yes.
You can see that kx equals to 0. The eigenvalues along y are minus and plus. And then if I look at minus and plus eigenvalues here, they have to be induced by a p orbital at the mid-bond position.
Yes.
And since I choose this direction, they're induced by a mid-bond orbital here.
And why not 1D? If this is in the, because you don't have information.
It could be 1D, or yes, yeah. You're right. It could be 1D, and I could check that by doing it in the y direction. Yes, exactly. Exactly. Yes, you're right. Thank you. You're right. Yes. Sorry?
You wind here in the kx direction, but if you have a 2D topological invariant, you wind in the whole torus.
Yeah. So this guarantees you that you'll wind in the other direction too. So you see, this actually, in terms of eigenvalues, has C4 symmetry. The eigenvalues are minus, plus, plus, plus. So if I did this in the y direction, I would get exactly the same. I would get exactly the same plot. Well, not exactly the same because I don't have C4 symmetry, but the same winding. Is that clear? That makes sense? Yeah. Yeah. So yes. Please.
You said that for trivial case, the real functions are localized, right?
Yes.
For topological case, they're not.
Well, that's one definition. You can define. You can. Yeah. You can. That's the simplest definition.
So, just how do I understand the non-localization from this plot?
Very good. So from this plot is immediate because you just have to remember that these plots are the plots of the PYP operator as a function of kx. Okay? And if I want to localize something, then I have to have two operators that, so this operator commutes with the Hamiltonian. Anything that's projected into something commutes with the Hamiltonian. Okay, so this operator commutes with the Hamiltonian. So I can certainly diagonalize both the Hamiltonian and this operator, which I've done. But in order to pin something, what I need to do is localize in 2 dimensions, 2 operators. Okay, PXP and PYP. So both the x and y positions in order to localize something. And if you do the commutator of these, you're going to find out that the commutator of this is exactly the winding. Okay? The Chern number is the commutator of this. But basically, it's already clear that you cannot localize it just from this plot, because what you see is that the eigenvalue of y, as I move kx from 0 to pi, goes around in the unit cell. So it doesn't really, considering that I have more than one unit cell in the system, it doesn't really stay in the unit cell. So this is a very good question, because now this lets me go to the Chern number. So let me just plot the next unit cell. I'm just going to plot the next unit cell, really. Okay, this is the next unit cell. This is just the first unit cell. This is the next unit cell. And the plot is repeated in the next unit cell. Let me plot the next unit cell. And the plot is repeated. So you can now see that basically as you move k from 0 to pi, what you're doing is you're taking one state, it's like a register. You're taking one state, moving it up, and moving it all the way up. So you're taking one state from the bottom of the sample and moving it to the top of the sample, which is the quantum Hall effect. So anytime you have winding in the Wilson loops, does that make sense? Yeah. Very good question. So basically, the immediate thing is when you have winding in the Wilson loops, any type of winding that goes outside the domain, then you have you cannot linearize it. You cannot make, because you have a next unit cell, and then your state when you wind, it just go to the next unit cell and to the next unit cell. It does not stay in the unit cell. Right? So that's clearly not possible to localize them in the unit cell. If it looked like, so for example, if I had a band that's like this, plus, 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 then my Wilson loop here would be 0, plus, plus, and here at kx equals to 0 would be also 0. So it could look like this. Okay? And this stays within the same unit cell, the Vanier center. Very good. Questions? More questions here, please.
Can you make sure that it doesn't wind twice?
It can wind twice for Chern number 2. With these inversion eigenvalues, it cannot wind twice. So with this inversion eigenvalue, this is the end.
But I was thinking you just drew this like 0, 0.
It can wind 3 times.
Yeah.
So this is also a very good question. So with this inversion eigenvalue, so inversion is kind of like a mod 2 thing. So it gives you the Chern number mod 2. It's not capable of distinguishing even Chern numbers, as I'll show very soon. And it's not able to distinguish between different odd Chern numbers. For example, let's make this with the same inversion eigenvalues. The thing is, with these inversion eigenvalues, I only know what's happening here and here. Right? So I could have this. Okay, this has to be continuous, so it's here. Right? And then on this other side, I would have inversions. I would have this and this. Okay? But it still winds an odd number of times. Does that make sense?
Yes.
Very good. Yes?
So instead of inversion, you had something like 3-4 rotation?
If I had 3-4 rotation, I'd be able to, well, the Briand zone would not be this, would be a bit 120 degrees, and I would be able to distinguish Chern numbers mod 3 by all of these means. So you see, I'm not able to distinguish the full Chern number, but I'm able to distinguish if a Chern number is non-zero by the symmetry. And the symmetry, the elementary band representations basically give you a set of bases for the atomic limits, and anything that's not an atomic limit is topological. And the set of elementary band, it's identical to the strong topological indices in a higher form at their lowest level, at the lower level of representations. There's more to elementary band representations, which are Berry phases, which I don't know if we'll get in. Yes?
Can you redraw the trivial trajectory of the values?
Yes. The trivial trajectory corresponds to any of these bands. So let's pick this one, the simplest one, with eigenvalues, right? So can you help me do it? So just help me do it. So this is a trivial band, eigenvalues plus, 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 plus. Well, I don't know if it's trivial band, but at least it can have Chern number 0. It can actually have Chern number 2 also. But let's take it to be a trivial band. Inversion cannot tell me if it has Chern number 0 or 2. Okay, so we'll take it to be a trivial band. So, and what are the inversion eigenvalues at kx equals 0? Plus plus. So this is what orbital at kx equals 0? It's a s orbital. Wilson eigenvalue. So it's here. Yeah? At pi, what is it at pi? It's also 0 at pi. Right? So now I can connect these 2 points. The trivial way of connecting them is something like this. And by inversion, I do something like this on this minus on 0 to minus pi. Yeah? Once you do this, there's two points. Okay? You have to connect them by a line. There's no other way. And I make this line a bit curved. Okay? And once I know the half connection, I find the other one by inversion. Yes? And you can notice that here the Wannier centers, as you move kx, stay within the same unit cell. So you can localize them. They don't move across unit cells. Okay. Very, very good. Now, let's do a more complicated case. So we've established how to, and it's pretty clear that this thing of elementary band representations and checking whether you can have, you know, linear combinations of them can be extended to all space groups for all symmetries, and it's useful in terms of finding out if zero is topological. Let's look at the following thing now. 2 occupied bands. Okay? And I want inversion eigenvalues to be these. Okay, so say I want 2 occupied bands of those inversion eigenvalues. I can certainly get them. I can certainly write a model that has them. If you're into masochistic things as writing tight-binding Hamiltonians, you can certainly do it. It's not even that masochistic. It's very easy to write this. So just 2 negative inversion eigenvalues. You're going to help me find out the Wilson loop of this guy. So this is, again, gamma xm. Gamma xm. Thank you. So I claim that this Wilson loop is also non-trivial. So let's find it. I'm going to draw the Wannier center as a function of kx. What are they at kx equals 0? So at kx equals to 0, I have a 1D system that's inversion symmetric because eigenvalue is minus minus and plus plus. What is the only way in 1D I can get eigenvalues minus minus and plus plus? Huh? What is it? Which one? Minus minus and plus plus at gamma and y. This guy, right? Minus minus and plus plus. 2 of these. Is that clear? There's just 2. One is so this guy. This is the pi, right? This is this point, right? So it's minus plus is this p orbital. Another minus plus this other p orbital. So I have 2 p orbitals. Nah. I have 2 p orbitals at the.
20 minutes.
Yeah. What are you doing?
What?
God.
I'll continue.
Yeah, still 4:30. This is the Israeli precision. Okay, so where was I? Yes, thank you. Thank you. Okay, so here I have 2p orbitals at 1c, right? What are they? So I know I cannot hybridize them because I need SMP to hybridize. So I know their Wilson loop eigenvalues are what? 2 pi's. Well, not 2 pi, but I have 2 eigenvalues at pi. Yeah? Is this clear? How about here? I have plus, 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 plus. What are these? At k is equals to pi. What are these? S1a and S1a. They're just these guys. Yeah? Is this clear to everyone? So what are the Wilson loop eigenvalues here? 0, because they sit, okay? All right. So now, how do I, does it make sense? Okay, so now what are the possible ways of drawing things? Well, I have a possible way of drawing things where I connect this with this and this with this. These are degenerate here, there's two degenerate here. They don't need, well, I didn't draw them degenerate. Shit. It's like this, yeah? Yeah, that's one possible way. Yes? And what would it be in this quadrant? Not quadrant, but in this half. It would be the inversion symmetry case. And this is what? A Chern number 2 band. Well, two bands, both of them having Chern number, well, the sum of them having Chern number 2. Okay? That's two bands, the sum of them having the Chern number 2. That's what that is. But notice there's another way of drawing them. And that's why with this set of eigenvalues, you cannot say that the Chern number is 2. You have to make, here there's only one way of drawing them. With these eigenvalues, the only one way is this. But here there's another way of drawing them. And let me draw them. I have 2 here, 2 here. What's another way of drawing them? Very good. So I can draw one like this, and I can draw another one like this. It goes here, the same one, yeah? And I just have to make sure that there's the symmetric. Is it clear why I drew this? So just ask, because it's better not to go. It's better not to go gloss over these. Well, I don't know what's better. Is it clear that those are the two ways of drawing it? So what I know, the fundamental things that I know from symmetry, is that I need to have 2 Wilson loop eigenvalues here at pi, because this is minus minus plus plus, and 2 Wilson loop eigenvalues 0 here because this is plus plus, this is plus plus. Yeah? This I know from symmetry. And now I ask, in between, how can my Vanya centers move as a function of kx? Symmetry does not impose a constraint in between because symmetry relates kx to minus kx. Okay? Inversion relates kx to minus kx. It imposes symmetry in how the spectrum looks between kx and minus kx, but it doesn't impose any symmetry here. It imposes symmetry at kx equals to 0 because it sends kx equals to 0 into kx equals 0, and this is a 1D system. It imposes at kx equals to 0. It imposes the symmetry at kx equals to pi because this is a 1D system. And then I found out the Wilson loop eigenvalues at 0 and pi, but now there's 2 ways of joining them. One way that gives you a Chern number 2, which is this guy, and one way that gives you Chern number what? So yes, I can choose, this, since this is periodic, there's a double degeneracy here, so I have to have 2 states coming here. But I can choose one to connect here, and double degeneracy here, and one to connect down, and I just do the inversion symmetric one. Yeah? Who's confused? There's no, nobody's going to do any harm to you if you're confused. If not, so just tell me now. Nobody's confused? No, it's fun. Yeah, thanks.
So the Chern number 1 case, right? Which looks a bit like that.
But it's Chern number.
Yeah, so it's more the other.
Yeah, it's just Chern number 2. Yeah, because this was singly degenerate.
So is there an argument why you cannot connect them in the opposite way?
No.
Yeah.
Yes, you're right. So basically, there's no. You can connect them in the opposite way, but they will still give you a Chern number.
Yeah,
but because so the Chern number is equal to 1 mod 2.
Yeah, exactly.
That's the fundamental thing.
Yeah.
So you're right. There's other connections. So this is the other connection.
Yeah, exactly. But you still get the same result.
But you still get the winding. So the point is, this is still a topological phase. To determine exactly what the Chern number is, you need to do more work. You cannot just determine it from the eigenvalues. Very good question. Any other question? Yes?
So you said this is a model for the churn insulated?
This is, well, this is a churn band, yes. And I drew, with inversion symmetry, this is a churn band of churn number 1, or minus 1, or 3, or minus 3. A band of 2n plus 1.
In general, churn insulated was regarded inversion symmetry, so
Exactly. Exactly. Very good point. So, very good point. With inversion symmetry, though, you can predict the fact that this is a churn insulator just by looking at the high symmetry points. So, so if I didn't have inversion symmetry, I would need to compute churn numbers, which requires the Wilson loop. That's how it's done. You don't compute the churn number through the integral. Nobody does this because it's just not done. But you compute it through the Wilson loop flow. But that requires knowing all the eigenstates everywhere. Whereas if I just have the high symmetry point states, eigenvalues here, I can immediately tell you that this is not an atomic limit. Does that make sense? Sorry, there was another question there.
So, in this case that we have inversion symmetry, having term number even means that our system is not topological.
No, it means that inversion won't detect it to be topological. So you see, this it's not an if and only if. If you have churn number even and inversion, then inversion won't detect that you have a churn number even. You could have a churn number even of 0. But the point is this program goes the opposite way. This program goes the way that if you find a band that's got odd number of minus inversion eigenvalues, then you know it's topological. If I find a band that's got even number of negative eigenvalues, I need to do more work. Okay, to find out if it's topological or not. I need to do the Wilson loop.
Okay, but if you have a topological system, then you compute the Wilson loop.
Wilson loops so far have detected all the known, that's the conjecture, but Wilson loops so far can detect all the types of topology that we can have in band structures so far. But Wilson loops are much more time consuming to compute because you need all the k points. Okay? So that's the major advantage of one of these things. Yes?
This case is trivial because you can...
This case is what?
The case here as a term number 0. Because you can
Which case?
bottom right.
This,
No, bottom.
this guy.
Yeah.
This is churn number 1. Sorry. This came out of me drawing two things. This is churn number 1. Yes?
Yeah, but...
This has churn number minus 1 or whatever. Okay? And together, like this, they have churn number 0.
Because you can choose a path without anything.
Well, now you still leave the unit cell, but there's no full winding. Okay? The churn number requires that churn number is a definition. Okay? It's the Hall conductance of the quantum Hall effect. Okay? So it requires that as I move flux, okay, I'm moving one electron from one side of the sample, as I thread flux into the sample, to the other side. And that requires you to leave the unit cell in a chiral way, like a tire-bouchon. Right? Whereas if I have this, what I'll do, this still leaves the unit cell, right? So this is, by the way, equivalent to this, right? Yeah. Because this. So what I'll do this still leaves the unit cell, and that's why it's not Vannierizable. You cannot make Vannier states if I have the Wilson loop. It's still topological. And look how it leaves the unit cell. It leaves the unit cell. These are crossings that you cannot... Shit. Okay? It leaves the unit cell. You can see it, right? But what it does, if you thread flux, is it moves one electron from this branch up, but it takes one electron from this branch down. Right? So it moves one electron up in this branch and one electron down in this branch. So that means that the net charge that it brings to one edge is 0. So that's why it's not a churn. Indeed, this is exactly how the Wilson loop looks for a quantum spin Hall. However, very good. A Wilson loop for a quantum spin Hall with inversion symmetry, it would be indistinguishable from this. Indistinguishable. Well, it would be indistinguishable from this. It'll be distinguishable from this, because with time reversal, you're going to have particle hole symmetry in the Wilson loop. But that doesn't matter. The winding is the same as the quantum spin Hall. But here, I don't have the symmetries of the quantum spin Hall state. I didn't put time reversal. So I don't have the symmetries of the quantum spin Hall state, but I get a Wilson loop that winds the same. So this is a different topological state. It's not the quantum spin Hall state. And we're going to find out what topological state it is right now. If the chairman gives me another 10 minutes that I actually have. I'm kidding. Okay. So, let's ask, so this is a Chern number 2 state. Chern number 0. Okay? And I don't want to look at this state. I don't particularly want to look at Chern numbers, you know. This was just for the purpose of showing you the simplest way. Okay? And as was very nicely pointed out here, I'm just going to draw it like, you know, in general, these don't need to be, with just inversion symmetry, they don't need to be the mirror of one another. They would look like I drew them before, but let's just draw them like this. And as was pointed out before, this is exactly how the Wagner centers would look in a quantum spin Hall state. But this is not a quantum spin Hall state, because quantum spin Hall states need time reversal to be well defined, whereas this one does not have time reversal. So what kind of a state is it? Well, it's clearly topological. For 2 bands. So this was in an older paper with Taylor and Emile Prodan, this observation that the inversion eigenvalues basically give you everything about these bands. Okay? So this is topological for 2 bands. Okay, but now let me add 2 trivial bands to the system. So add on top of these bands okay. So add on top of these 2 bands, add 2 trivial bands. So now, yes. Yes. Okay, good. Yes, thank you. Thank you. Okay, so now we're going to add 2 trivial bands. So we're going to look at the system formed by inversion eigenvalues, minus minus, plus plus, plus plus, minus minus, sorry, plus plus, which is Wilson loop winding like this, yeah? And now we're going to add 2 other bands, which have inversion eigenvalue plus minus, plus minus, plus minus, plus minus. So I've added to this system, I've added minus minus, plus plus, plus plus, plus plus. I've added 2 bands with minus plus, minus plus, minus plus, minus plus. Yeah? Okay. Are these bands an atomic limit, the bands that I've added?
Yes.
They're atomic limit, exactly. You can actually even find them somewhere. They're, I can get to, well, they're an atomic limit. Okay, I can have their yes, please tell me. S1A plus P1A. Yeah, okay, very good. Yes, thank you. Exactly, they're S1A plus P1A. Thank you. Okay, so these bands that I've added are atomic. Okay, and I've added them to a topological, because this has Wilson loop winding. Okay. By the way, is this an atomic limit? It's not, because it has Wilson loop winding, clearly. So it should not be written down as a linear combination of these bands. Yes?
Sorry, the trivial band you added is twice the same.
Wait.
values, right?
No, trivial band I added plus minus. So I added S at 1A and P at 1A.
Yeah, but if you look at the 4, it's,
So I've added, is it good? So I've added this. Okay, now let's look what this means. What are the Vanya centers of the trivial band doing? Of the trivial two bands doing? What are the Vanya centers? How do I draw the Vanya centers of the trivial two bands? What are they? We got to hurry up a little bit because I don't think we're getting to graphing. But what are the trivial bands Vanya centers doing? Say at kx equals to 0, and kx equals to pi. What are they? At kx equals to 0 of of these bands, plus minus, what are they? But what did we say about plus minus? They can be SP hybridized. And what are they really? Generically. Theta minus theta. What are they at kx equals to pi? Chi minus chi. Okay? And in between them, they're trivial bands, so they're not going to wind. They're not going to do anything. I draw them like this. Yeah? That's what they do. Is it clear? So the way I know that it's theta minus theta here is they have, at kx equals 0, they have plus minus eigenvalues, which we said is an s orbital plus a p orbital at 1a. But s and p orbitals at 1a can hybridize. If I just turn on some parameters, they can move away from the origin. They can move all the way to 1b. So they have generically theta minus theta. Yeah? So now let me add this guy to this guy, which is what I do when I add these two. I'm going to first add them as just blocks and then turn on the coupling between them. So if I just add these two Hamilton, if I just add to this the band that does this, which is this band, okay, to the band that does this, I add these two trivial bands, okay? So if I add them without any coupling, just block diagonal, make the Hamiltonian block diagonal, then this guy will do this, right? Yes? I just added to this. I get this. Is it clear? What will happen now if I turn on coupling? So this is a physical interpretation that as you move momentum, the Vanya centers in the unit cell do this, right? The center of charge, as I tune this parameter momentum, the Vanya centers in the unit cell, they first go like this, they go through the unit cell, but then, you know, you have, if I was to draw them in the unit cell, they do this for this case, and for this guy, they do this, okay? But there's some points at which the Vanya centers collide. And these crossings are protected by what? What symmetry do I have at a generic point there? Nothing. They're protected by nothing. So what do? They gap. This is when I couple the models now, exactly. Generically, they have to do this. And I urge you, you can take one of these models. It's not hard to build. You can just take a 2D quantum spin hole and break time reversal on it, and it's with inversion. And it's got inversion eigenvalues, and you can just add trivial bands to it. And they do this. Yeah? So now what have I done to the Wilson loop winding? I've added two trivial bands, and I've transformed the Wilson loop winding that was winding to a Wilson loop winding that doesn't wind. Okay? So these type of phases that existed with this inversion eigenvalue things have been given the name by Poe et al. Fragile phases. Okay? So these are the so-called fragile phases. Well, this is the simplest model that I can build for a fragile phase if you want. Okay? Who are you? Okay, this is the simplest model I can build for a fragile phase, where if you take a topological phase and add trivial bands, you get to a trivial phase. Okay, this is very weird, right? Normally, but the reason why you do this is that this phase that you started off has no strong indices. So remember I was telling you the strong indices, like Chern number, they protect crossing. So for example, if I just had a Chern number, if I just had this winding of a Chern number and added another trivial band, okay, another 2 trivial bands, and did the same thing that I do here, Chern number wouldn't care. Okay, you can see it. It still winds, right? You start like this, you go like this, you go like this, you go like this. The Chern number doesn't care. But if I have this state where the winding is in this form, this state cares if I add trivial bands. Is it clear?
So how is this fragile topology different from a weak TI?
A weak TI would also not care if you add. A weak TI is a strong. So the weak versus strong names that we talked about are basically like kind of like historical also. So all the weak TIs actually have strong topological indices, in the sense that you can add any bands to weak TIs, and as long as you keep the symmetries, you cannot stop the Wannier flow in some directions. Any weak TI, so all the weak TIs, all of those have strong Wannier, have strong indices. Okay, so now let me just one more minute. Just hold your horses. You stop me with the Okay. So now I said, I said that, oh, well, this state, I said that this state cannot be written in terms of linear combination of these. And you'll indeed find this true. But but linear combinations with what? Well, it cannot be written in terms of linear combinations with positive coefficients. So I want you to check that this state, okay, is equal to P at 1C plus P at 1B plus S plus S at 1A plus P at 1D minus, and this is important, S at 1A plus P at 1A. So in terms of eigenvalues, this state, which has eigenvalues, so this state here had eigenvalues minus, minus, plus, 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 plus. If I take that linear combination of these things, then these eigenvalues are equal to this. So this minus is kind of fundamental, okay, in the sense that it tells you that this state cannot be written as a linear combination of states. It needs the minus. But this tells you the same thing as having this plus S at 1A plus P at 1A, which are just these two. I added these two bands. This has now become a sum of trivial bands. Okay?
Why do you need positive coefficients?
Sorry?
Why do you need only pluses in your linear combination to do the atomic limit?
Very good, because minus is not an operation that you're allowed to do in a Hamiltonian, right? You cannot just take out orbitals. So this is just math stuff, right? Where I take out bands, but normally I'm not allowed to take out bands, right? So okay, so now there's one last thing before time kills me. This state, even though I've added bands to it, so it's topological if I have two bands. It's trivial in terms of being Wannier-Reisel if I add two bands to it. So if I make it 4 bands, I have to add the right bands though, actually. I have to add these ones. You can see the whole loop. However, it still has a stable index, which is the number of crossings of the pi. And this is called a Stiefny-Whitney index, and it's the same index that actually graphene has, the graphene bands have, and I'll hope to get there next talk. So.
Questions?
Come on. There's got to be a question.
Great, no problem. Any questions?
So when you added the two trivial bands, so you said they were like S1A and P1A.
S at 1A and P at 1A, right? To get these eigenvalues.
Okay, but couldn't they be any other SNP pair? If I look, they can also be like.
Yeah, they could. Yeah. In this, well, yeah. Well, they could be any other S&P pair like this. But it couldn't be it couldn't be the S from here. And yeah. They could. They could. They could. You're right. So in general, there's some bands that you can add to make this not have Vanier states. Not all the bands that you can add. So if I added, you can work this out. If I added this S and this P, they will still be winding in the Wilson loop. It's only these particular, so these two, or these two, or these two, or these two. So only a particular set of bands can make your state trivial, but there's a particular set of bands that make your state trivial in terms of Wilson loop flow. And this has to do with the bands that you subtract on this side. You know, I can write this as a subtraction, right? Or I can add this. But there's something stable left over, which is the number of crossings of this guy here. Okay? So any of these bands that I add would still leave these crossings here. And this is a determinant of a Berry phase. So if I now do the Wilson loop of these, so Vanier, I would get -1, etc. Yes?
So you said that strong indices can be broken by fragile.
Strong indices can never be broken.
Right.
Cannot.
Right. So C equals 1 was strong and C equals 2 was weak.
No. C equals 2 is still a strong index. Okay? It cannot, so C equals 2 is a strong index. It cannot be characterized by inversion. Like inversion, if I have certain inversion eigenvalues, I cannot tell you if C is equal to 2 or C is equal to 0. That's the fundamental thing. I need more information in which, I cannot tell you that C is equal to 2 and C equals to 0 just from the inversion eigenvalues at high symmetry points. But I need more information to compute C, which I need these Wilson loops. If I have C and it's 2, that's a strong index.
Okay, so when you work with like Chern numbers, odd is always strong and then...
Chern numbers are always strong. Yeah, Chern numbers are always strong.
And non-zero, okay.
And there's a set of indices that are always strong. So basically the set of indices that's strong is the set of indices that cannot be expressed as linear combinations with both positive and negative coefficients of atomic limits. The set of indices that is fragile is described by linear bands that are topological, but described by positive and negative coefficients. You have to have a negative.
But can you know a priori what's stronger or weak, or do you have to check and then...
Well, so I don't like the weak terminology, because the weak terminology was invented basically when we didn't know the plethora of topological phases. The weak terminology was invented. So all the weak indices are actually strong, in the sense of not... The weak indices as they were defined, in my definition, which you may or may not agree with, they're called, I call them strong because they're also not Vanierizable.
But I mean like strong and non-strong.
Strong and fragile.
Can you know a priori what's what, or do
Yes.
you check everything?
Well, you need to check them. But you need to right. So for example, from this one, if I have 2 negative eigenvalues here and 3 positive, I would immediately know that it's not a strong index, because I wouldn't even need to do the Wilson loop. The Wilson loop is to show you that you can add bands and you can stop the winding of the Wilson loop. I would immediately know that it's not. That I would know that it's not strong, but I would know that it's not trivial, because you can never write this as a linear combination of positive coefficients of this, but you can write it as a linear combination of positive and negative. Yes.
So also a terminology question. So you say this is has no strong index, but so the Stiefel-Whitney is a weak, no, sorry, a fragile index.
Well, no,
You said it's an index,
the Stiefel-Whitney is the stable index. It's not a, so it's got a fragile index, which are just these negative, the negative inversion eigenvalue is mod 2 at one symmetry point. Right? So this is a fragile index because I can add bands.
Yeah.
See, the negative inversion eigenvalues at one symmetry point mod 2 is a fragile index. I can add bands and change it. Right, okay? But the fact that this has, so just, even if I added 4 bands, or I have these 4 bands, and I would look at this system, and I would ask, well, the Wilson loop doesn't wind. How do I know that within this system of bands, there is a subset of 2 bands that's topological? Right, so the question is, I have this system of 4 bands. It doesn't wind, so you'd say, oh, it's trivial. Well, the moral of the story is that just by looking at it, I would know that there is a subset of 2 bands of this system that's topological for which this winds. And the way I would know it is by looking at this guy. At the Stiefel-Whitney index is just this crossing here. Mod 2.
But it is the fact that you have this number of this high eigenvalues.
Yes, it is. Yes, it is the fact that yes, it's related. Yes.
Another terminology
right.
question: is there a difference between topological indices and topological invariants for you?
Well, for me, you see, like all this stuff is kind of flowing, right? As the terminology for me is a bit messed up. But what I say is strong indices are non-linearizable. Stable indices are indices that can be defined even for fragile phases that tell you if a phase is fragile. And then there's all these other indices like inversion eigenvalues, which are actually just representations, and you can change them by adding bands. So I would say there's strong indices and there's stable indices. Strong indices are obviously stable, but vice versa is not. Stable indices are not necessarily strong. But I don't know. People might not agree with this terminology. So, in fact, I'm the only one that agrees with it.
Maybe one last question. So about this, this weak strong thing is confusing, but let's say in the old days when this all was not there, this strong weak invariance, as far as I understand, in Folker was associated with stability to disorder. Right? So like when you or other this difference between a torus and a sphere, right? So in this sense, do you think about this weakness of your indices, or
So you're right. So historically, weak indices are associated with indices that need translation invariance,
right?
Which is disorder. Yeah. So you need the weak indices are indices that need translation invariance, etc. The reason why I don't like that terminology is because there's indices now that are associated with rotational symmetries, for example, or other types of symmetries that are also that would also be called weak in a sense. So then you've got like this massive chopping block where strong indices are only 3 of them: the Chern number, the quantum spin Hall, and the quantum spin Hall in 3 dimensions. And you got all these other things that are still non-linearizable, but they're called weak. So it's not a proper kind of in my view.
Do you think if you have a disorder that breaks on average, breaks the rotational symmetry?
Yeah, if you have a disorder that on average breaks the rotational symmetry, a lot of this stuff is gone. Well, if you have a disorder that breaks on average inversion symmetry, a lot of the stuff is gone.
Is all of this stuff gone?
The Chern number is not. Right, but most of the rest is. If it breaks on average, if it doesn't break it on average,